Hello, I am Taza Amsha from Group 2-7 together with my group mates to present about our integrated design project. First, let me start with Reaction Engineering 1. This part will cover the description on how the chosen reactor separator system works, type of the reactor and catalyst used, the sizing of the reactor and the strategy to maximize the selectivity and yield of hydrogen gas and minimizing the side reaction. Steam methane reforming technology involved the use of mixer, heat exchanger, packed reactor for SMR and WGS reaction, and a cooler. The purpose of the mixer is to mix natural gas and steam before entering heat exchanger. Once the mixer flow through the heat exchanger, it will be heated up to the temperature of the inlet PBR. In the first PBR, methane will react with water to produce carbon monoxide and hydrogen. This reaction is called SMR reaction. After that, the cooler will cool the mixture to the temperature of the inlet PBR for WGS reaction. In this PBR, carbon monoxide that was produced from SMR reaction will be used to react with water to form another batch of hydrogen and carbon dioxide.
To design a successful SMR technology, fixed packback reactors are favored over other reactor types due to their simple technology. Besides, PBR has a low operational cost as it is a continuous operation and requires less usage manual labor. Hence, two packback reactors are utilized, in which one of them being used during the steam methane forming and another one in water-gas shift reaction. This reaction is assumed to be a steady-state reaction with perfect mixing, in which there is no special variation in radial direction, resulting in constant temperature, pressure and catalytic activity. Next, gases are assumed to be ideal and there is no side reaction. For SMR reactor, the catalyst needed is nickel oxide as it is able to perform well under cyclic redox conditions of chemical looping steam reforming, as well as in tandem with high temperature. The catalyst is supported by aluminium oxide as it was discovered to have high reactivity and no agglomeration towards the reaction. The volume of the reactor are calculated using 5 steps method. Firstly, mole balance, which derived from the general equation. Secondly, rate law, which calculated using formula from literature using zoo and Forman kinetic parameters. After stoichiometric table is generated, the formula is combined as a curl and a string. The last step is to evaluate the formula analytically to get the weight needed for SMR, which is 262.72 kg. The volume of catalyst can be calculated by dividing the weight with density, and the gas hourly space velocity from literature are used to calculate the volume of reactor, which is 0.614 m3. For water gas shift reactor, the catalyst needed is iron oxide as it can withstand high temperature, cost-effective and environmentally friendly. The volume of the reactor are calculated using 5 steps method. Firstly, mole balance, which derived from the general equation. Secondly, rate law, which calculated using formula from literature using zoo and Forman kinetic parameters. After stoichiometric table is generated, the formula is combined as a curl and a string. The last step is to evaluate the formula analytically to get the weight needed for WGS, which is 98.71 kg catalyst. The volume of catalyst can be calculated by dividing the weight with density, and gas hourly space velocity from literature are used to calculate the volume of reactor, which is 1.501 m3.
Next is the strategy to maximize selectivity and yield of hydrogen gas. The first one is by increasing the concentration of methane in SMR reaction, because the stoichiometric number of H2 in reaction 1 is 3 times more than the stoichiometric number of H2 in reaction 2. Raising the concentration of CH4 in reaction 1 will increase number of mole of H2. Next is by increasing the inlet temperature entering PBR and in SMR reaction. SMR reaction is an endothermic reaction, and since endothermic reactions favors high temperature, therefore by increasing the entrance temperature into PBR in SMR reaction will improve conversion and H2 yield. Next, decrease the inlet temperature entering PBR in WGS reaction. WGS reaction is an exothermic reaction which favors lower temperature. The lower temperature in reaction 2 will increase the conversion and the yield of H2 since it will be produced more under low temperature condition. The selectivity of the desired product H2 will also increase. Next is by increasing the concentration of water. Since water acts as reactant for SMR and WGS reactions, the higher the concentration of H2O means the higher the concentration of the reactants for both reactions, which will undoubtedly enhance the yield of H2 as it will be produced more when the concentration of H2O is lower. Lastly, decreasing the inlet pressure in SMR reaction will not only affect the selectivity and the yield of hydrogen gas, but will also minimize the side reaction, because the pressure helps limit the energy contained inside the reactant molecule of the side reaction. Therefore, the side reaction barely occurs since the reactant molecules cannot achieve the activation energy of the side reaction.
Now let us move on to CE-V2-053 part of the presentation. The objectives of this part is firstly to simulate the reaction process of hydrogen production using the symmetry software. Secondly is to validate the simulation by comparing with the manual calculation from CE-V2-043. And lastly to perform sensitivity analysis despite discussing the effect of temperature, pressure, feed flow rate and composition. Some of the assumptions made to simplify the model includes firstly the whole process inside the system is in steady state. Secondly, the composition of the natural gas stream is 100% maintained. Next, side reactions in SMR and WGS are neglected, and lastly, the reactions involved in system are elementary reactions. This is the process flow diagram of the hydrogen production process. Streams of natural gas and steam are supplied at temperature of 300 degrees Celsius to reduce the duty of the heat exchanger, so less heat is needed to increase the temperature to 700 degrees Celsius. Despite that, steam is supplied in excess, so further reaction can occur in the WGS reactor to produce more hydrogen. Steam and natural gas are mixed and fed to the heat exchanger since the reaction of steam methane reforming is highly endothermic, so heat energy is needed for the reaction to occur at constant temperature. In SMR reactor, water will react with methane to produce carbon monoxide and hydrogen. After that, temperature of the reaction mixture is reduced to 400 degrees Celsius before it is supplied into the WGS reactor, so the carbon monoxide and water can further react to form carbon dioxide and more hydrogen.
The deviation errors can be calculated by comparing values made from manual calculation from reaction engineering course with the value from symmetry software. The values which will be going to evaluate are outlet molar flow rate of each component as well as conversion value from SMR and WGS reaction. The conversion value can be calculated by dividing molar flow rate reacted with the initial molar flow rate as shown in the screen from the symmetry software. Then, the deviation error is calculated by using the formulas which is circled in red right now. It can be seen that there are some parameters that has a really high deviation error. This is due to the difference in formula to calculate rate law. For manual calculation, the rate law is taken from literature by using zoo and Forman kinetic parameters, while the simulation calculate the value of the rate law by assuming that the reaction is elementary reaction. However, for solid catalyzed reaction, the overall order of the reaction is not an integer, as the rate law supposed to be used is non-elementary rate law.
Sensitivity analysis is carried out using the case study function in symmetry, having the main desired product of this whole reaction is the hydrogen. Flow rate of hydrogen and its fraction in outlets of SMR and WGS are determined as dependent variables during this analysis. Firstly, for pressure sensitivity analysis, as pressure of steam is increased from 100 to 1500 kPa, the line graphs are nearly stagnant, which means even a significant increase in the pressure of steam and methane will not really affect the yield of hydrogen. Hence, it is preferably to maintain the pressure as low as possible but not too low until the hydrogen yield is reduced extensively, considering the worker's safety and it is cost saving. It is also deduced that the results obtained in both graphs are of the same values. This is because as pressure of one of the streams is increased, both streams eventually enter a mixture, where new pressure and temperature is generated. For temperature analysis, the temperature of the feed of SMR reactor is chosen as independent variable since it is directly connected to the reactor. Based on the graph displayed, it is concluded that temperature is increased. The production rate of the hydrogen in both SMR and WGS will increase as well. Theoretically, by referring to Wojcik et al. 2018, as temperature is increased, the hydrogen yield in WGS should decrease. This is because high temperature would limit the reaction equilibrium, resulting to more formation of carbon monoxide. However, the results obtained in the simulation are against the theory due to inaccurate activation energy and pre-exponential factor assumed, as well as inappropriate feed conditions. Although as temperature increased, the hydrogen mole flow rate increased due to the elevated reaction kinetics, hence producing more product. Moving on to the feed flow rate sensitivity analysis, the graph shows gradually increasing trend for the mole flow rate of hydrogen at both outlets of SMR and WGS reactors as the natural gas feed flow rate is increased. This is simply due to increasing amount of reactant molecules to produce more products. Oppositely, increasing the steam mole flow rate will not increase the production of hydrogen in both SMR and WGS reactions. Referring to the graph, the most optimal flow rate in order to maximize the yield is 1450 kmol per hour. If further increased, it will no longer favor the reaction as the methane has become the limiting reactant. Lastly, for the feed composition sensitivity analysis, we decided to have steam to methane ratio instead so we can evaluate the ideal ratio in producing the highest amount of hydrogen. According to the graph at the left, when the ratio increased to 3.5, the fraction of hydrogen at SMR outlet is the highest, while at the WGS outlet is around the ratio of 5.5. This means that the range for the optimal ratio for the reaction in SMR and WGS would be in between 3 to 5. Based on the graph on the right, at the right side, it is deduced that the ratio and the methane flow rate is inverse to each other. This is because higher steam to methane ratio means more steam is supplied in excess. Hence, more molecules of methane will react with water until eventually leaving no residue left in the outlet of WGS reactor. This explains why beyond the ratio of 6, the line graph is approaching 0.
Assalamualaikum, my name is Nofarisha Aina and I will continue the presentation on the separation process 2 part for the hydrogen enrichment unit, where we will cover the design of adsorption column, the design of separation unit, and the strategy to achieve 99.9% purity of hydrogen and regeneration process. First, we are going to explain on the design of adsorption column. Considering the stated assumptions, adsorbent chosen to separate carbon dioxide and hydrogen gas is activated carbon. This is because activated carbon is highly porous and have the strongest physical adsorption force. It also have the greatest adsorption capacity for carbon dioxide, which can result to a higher separation efficiency. Next, the type of isotherm used in the adsorption column is Langmuir isotherm at the operating temperature of 298 Kelvin or 25 degrees Celsius. Lastly, for the design of adsorption column, we are going to determine the MTZ, diameter and total height of the adsorption column. Shown below at the left-hand side is the concentration profile for adsorption in a fixed bed at various position and time, and at the right-hand side is the breakthrough curve of carbon dioxide for activated carbon. The value of TT and TU is found to be at 25 and 12 minutes respectively. In order to calculate the MTZ and diameter, a few assumptions need to be done, in which the total adsorption column height is assumed to be 2 meter, the volumetric flow rate is assumed to be 84 liter per minute, and the feed velocity is assumed to be at 0.6 meter per second. From the calculation, it is found that the diameter of adsorption column is 0.05451 meter. Moving on, the total length of the used bed calculated is 0.96 meter, while the length of unused bed is 1.04 meter. Since the mass transfer zone is represented by total length of unused bed, therefore the mass transfer zone MTC is also equal to 1.04 meter.
Design of separation unit. In this process of gases mixture separation, polymers are commonly used as membrane materials due to their attractive firm selective properties and high processability. In this process, a polymer composite membrane with polymer support is used that will provide support and mechanical strength to the membrane. This membrane material is chosen is because it can reduce stage cut when the working pressure increases. At the lower stage cut, the separation efficiency of CO and H2 will increase, which subsequently increase the recovery and purity of hydrogen gas. For the membrane type and configuration, hollow fiber membranes have small diameter, which is lower than 1.5 mm was chosen. The reason for choosing hollow fiber membrane is because it has a very large surface area within an enclosed system, which will result in increasing the separation efficiency. Other than that, it also uses up moderate energy, which can reduce the energy consumption. As this membrane can be manufactured in different diameters, hollow fiber module can be widely used for streams with different flow rate at low cost. Strategy to achieve 99.9% purity for desorption regeneration process. First, lowering the feed flow rate. When the feed flow rate is low, adsorbent will have enough time to interact with the surface of the adsorbent, and the adsorbent will be used up efficiently to adsorb the CO2 for removal process. Second, polybed H2 enrichment unit. It is found that raw H2 gas fed into the SMR hydrogen plant has lower hydrogen gas composition and higher impurity compared to the raw H2 gas fed to the advanced IGCC that is able to produce high H2 production at similar 99.9% mole H2 purity. Next, multiple layer adsorbent. This is because the usage of adsorbent with different characteristics can optimize the bed performance and hence increase the purity. Two-layer bed could result in a better performance compared to the bed performance when using the single layer. And lastly, temperature swing adsorption unit. The carbon dioxide removal process favors low temperature and high pressure by using the temperature swing adsorption unit governed by the Henry's law.
Lastly is the Gibbs refractive cycle. For the dissection part, this project is to design 30,000 tons of hydrogen gas with a purity of 99.9%. Next, the feeling throughout the journey is lack of interaction for the starting phase, and we recognize that some members were uncooperative. However, the ideas were shared between the members, which was quite good as the evaluation for this project's journey.
Next, we analysed that weekly meeting could have helped the progress, while teamwork among members and research articles helped us to route the IDP. Also, we concluded that the time management and sense of responsibility is important, and Gantt chart should be implemented for a smoother IDP session.